starting our program in a few minutes. So for our guests, you may take the back chairs here as we are not waiting for... Again. So good morning po once again. Pwede nyo na pong i-occupy yung ating mga vacant na leather chairs po dito. They're here to celebrate the 160th National and 75th World Meteorological Day. I am Joanne May Adelino.
And I am Christian Villalon. It is an honor to be your host for today's scientific forum. This year's theme, Closing the Early Warning Gap Together, underscored the urgency of strengthening early warning systems worldwide.
This theme resonates deeply with the Philippines, a country highly vulnerable to natural hazards. Today's discussions will highlight collective efforts and scientific advancements aimed at ensuring that early warnings reach all communities effectively.
Indeed. But before we dive into our discussions, let us begin this program with an invocation and national anthem. May we request everyone to rise.
Heavenly Father, we come to you today with humble hearts, seeking your guidance and wisdom as we begin this program. Lord, we ask that you would bless every person who has gathered here today, and that you would be present with us in a special way. We pray that this program would be a time of learning, growth, and fellowship for all of us. Help us to listen to one another with open hearts and open minds, and to support one another as we strive to serve you in all that we do. Please give us the strength and the courage to follow your will, and to use the gifts and talents you have given us to make a positive difference in the world. We pray all of this in your holy name. Amen.
Noon pa man, malaki na ang naging bahagi ng mga kababaihan sa lipunang Pilipino. Kaisa sila sa marubdob na paghahangad ng kalayaan ng ating lahi. Kabilang sila sa paglinang ng ating makulay na sining at mayamang kultura. Kasapi sila sa pagtataguyod ng mga adhikain ng kapwa mamamayan at sa pagtugon sa mga pangangailangan ng lipunan. Katuwang sila sa pagtuklas sa mga larangan ng agham at medisina. Kapanalig sila sa pagpapairal ng batas, karapatan at katarungan para sa lahat. Kabahagi sila sa paglilingkod sa bayan at sa pagpapanatili ng demokrasyang Pilipino. Sa paglipas ng panahon, hindi nagmaliw ang kanilang pag-ibig sa ating inang bayan. Mga kababayan, ito ang alay ng mga kababaihang Pilipino para sa bayan. Tumayo po tayong lahat at sabay-sabay nating awitin ang pambansang awit ng Pilipinas.
Once again, good morning to all our participants joining us here at the venue, and also to our online attendees in Zoom, as well as our viewers on Facebook and YouTube. Welcome to this year's Scientific Forum. We would also like to acknowledge the presence of the executive staff of the DOST-PAGASA, headed by our administrator, Dr. Nathaniel Servando. And we also have a visitor or a guest from the Philippine Navy, Captain Panol. Welcome to the DOST-PAGASA.
We are grateful to our esteemed speakers, partners, and all of you for joining us today. To formally open today's scientific forum, we have the honor of hearing from the Administrator of DOST-PAGASA, Dr. Nathaniel T. Servando. Let's give him a warm round of applause.
Pleasant morning to everyone, esteemed guests, colleagues, partners, and of course to our guests this morning, both physically and online. Foremost, our beloved Secretary, Dr. Renato Yusolidom Jr., who will be giving message virtually. Also online is Mr. Ben Churchill, the Director of the WMO Regional Office for Asia and the Pacific, together with Mr. Yoji Yamada. We have also here Mr. Chencho Dorji of FAO. We have also here our dear friends, no? To many activities related to the provision of climate information services, Ms. Hazel Tancholing. We have here Navy Captain Romel Marcelo Panol. I think your first time to come here or to attend this event. Okay. And of course, our friends from the media, we have here Mr. Ariel Rojas, and representatives from the different local government units, DRRM offices. Of course, our usual partners, agency in GCP, DNR in GB, DILG, NIA, ito yung mga kapitbahay lang namin, DA, PCA, and of course other agencies. And of course, the members of the PAGASA executive staff, mga division chiefs, not only in the central office but also from different regional offices, from the north up to the south. Of course, our colleagues in the PAGASA, and the deputy administrators. I think later on, Dr. Marcelino Q. Villapuerte will be joining us, ang deputy administrator namin for research and development. Our newly conferred scientist, one, Dr. Tasio Vasconcelio, pangalawang scientist namin. Once again, good morning. The DOST-PAGASA is pleased to welcome everyone to the scientific forum, one of the key activities for the celebration of the 160th National and 75th World Meteorological Day celebration. Naka-160 years na kami. It's because meteorological services started in 1865. Ang nag-umpisa nito yung mga Jesuits, priests. Prominent among them is Father Federico Faura. Kaya mayroong Faura Street. No? And of course, this year we adopted the WMO theme, closing the early warning gap together. The theme is a strong reminder of the shared responsibility to strengthen early warning systems to save lives and livelihood. And this is especially relevant to the Philippines, a country that is highly vulnerable to natural disasters. Alam na naman natin ito, no? Dahil sa ating geographical location, located along the typhoon belt and the Pacific Ring of Fire. Of course, hydrometeorological hazards like typhoons. Ito yung, plus of course, the Philippines as an archipelago, we face frequent and intense hydrometeorological hazards such as tropical cyclones, heavy rainfall floods, storm surges, and sometimes drought. As well as climate events, no? El Nino, La Nina, na nag-cause ng variability in our climatic condition in the Philippines. These hazards could cause potential disasters such as loss of lives, livelihoods, and damages to infrastructures, making early warning system not just a necessity, but also a lifeline, no, for the people. We at DOST-PAGASA continuously strive to improve our forecasting and warning capabilities. And one of the innovations, ito po yung palagi nyo naman na sigurong naririnig, and we hope we can fully automate operational na sooner. Ito yung impact-based forecasting, which goes beyond predicting weather conditions to assessing their potential effects on communities. By providing clearer, more actionable warnings, we help decision makers and the public prepare more effectively. However, closing the early warning gap requires collective actions from all members of the society. Lahat tayo may ginagampanan, hindi lamang ang PAGASA. We must work closely with local government units, communities, and partners to ensure that timely and understandable warnings reach those who need them the most. Let this forum serve as a platform for learning, collaboration, and strengthening our commitment to disaster resilience. Thank you for joining us today, not only those present here in this conference room, but also those attending online. And I look forward to a meaningful discussions that will help us build a safer, progressive, and sustainable life for every Filipinos. Magandang umaga po.
Thank you, Dr. Servando, for those insightful words. Next, we are honored to hear a keynote message from a distinguished leader in disaster resilience and geosciences. As a strong advocate for science-based disaster preparedness, he has played a pivotal role in advancing early warning systems in the Philippines. While he is unable to join us in person today, he has prepared a special message for this occasion. Let us now listen to the pre-recorded keynote message from the Secretary of the Department of Science and Technology, Dr. Renato U. Soledum, Jr.
A pleasant morning to all of you. It is an honor to join you today as we celebrate the 160th National Meteorological Day and the 75th World Meteorological Day through this scientific forum themed Closing the Early Warning Gap Together. This year's theme underscores the critical role of early warning systems in mitigating weather-related disasters, especially in the face of the climate crisis. Given its geographical location, the Philippines ranks among the most vulnerable nations to the devastating impacts of tropical cyclones. As extreme weather events become more frequent, the urgency for effective solutions grows stronger. As the country's national meteorological and hydrological service provider, DOST-PAGASA plays a vital role in mitigating the risks brought about by our rapidly changing environment. Central to our scientific endeavor is to predict, understand, and lessen the impacts of these weather-related events. Through the dedication of our meteorologists and climate scientists, we contribute to policy decisions that improve community preparedness and ultimately saves lives and livelihoods. In 2022, the United Nations launched the Early Warning for All as a groundbreaking initiative to ensure that by the end of 2027, everyone on Earth will be protected from hazardous weather, water, or climate events through life-saving early warning systems. In line with this global call to action, DOST-PAGASA has been actively developing and providing multi-hazard early warning systems for the Philippines. These systems are crucial in giving people time to evacuate, secure properties, and implement disaster response measures. To ensure that scientific and technological efforts maximize social and economic benefits, DOST formulated the Harmonized National Research and Development Agenda for 2022 to 2028. This agenda includes a strong focus on disaster risk reduction and climate change mitigation, aligned with the Filipino aspiration for safe, inclusive, resilient, and sustainable communities. It highlights the importance of multi-sectoral collaboration in disaster risk reduction, promoting synergy among stakeholders through research to maximize the impact of science and technology products for public welfare. This year's scientific forum theme, Bayanihan in Action, Strengthening Last Mile Early Warning Systems, encapsulates what we in DOST aspire to achieve. Recent research and innovations by DOST-PAGASA and collaborators from the scientific community and academia help enhance early warning systems for our communities. Inspired by the Filipino spirit of Bayanihan, we hope to foster stronger collaboration among the scientific community and various stakeholders in building a more resilient Philippines. After all, disaster risk reduction and management is not a responsibility of a few, but a collective effort across sectors. Let us remain united in our mission to close the early warning gap, not as individuals, but as one collective force, working hand in hand to ensure the safety and resilience of every Filipino, from urban centers to the geographically isolated and disadvantaged areas. As I always say, let us be victors over disasters and stop being the victims. With the correct information and active collaboration, we can all contribute to a future where we are not only resilient in the face of disasters, but also equipped to thrive and flourish despite the challenges we encounter. Thank you, and let us continue to move forward with renewed energy and a shared commitment to closing the early warning gap together. Have a productive forum to everyone.
Following the keynote, we are honored to hear a special message from the Secretary General of the World Meteorological Organization. As the first female Secretary General of the WMO, she has been at the forefront of global efforts to enhance weather and climate resilience through innovation and international collaboration. Let us now hear from Professor Celeste Saldo.
While we are waiting for the video, let me acknowledge our participants joining us here at the venue. So we have representatives from MIA, Meralco, Philippine Coconut Authority, DILG, FIVOX, Philippine Navy, ABS-CBN, the FAO, MGB, DENR, NPC, the Department of Agriculture, NGCP, and the multi-hazard impact-based forecasting and early warning systems, and PNO. So once again, let's hear it from Professor Celeste Saulo.
Dear members, colleagues, friends, happy World Meteorological Day. Happy 75th anniversary of the World Meteorological Organization as the UN authoritative voice on weather, climate, and water. Today, and indeed for the whole of this year, we celebrate the contribution of WMO and its members to saving lives, serving society, and protecting our planet. The staff of National Meteorological and Hydrological Services are like doctors and nurses working 24/7 to safeguard and promote public well-being. I would like to thank each and every one of you. We are more than just weather forecasters. Scientific data, information and services provided by the WMO community underpin decisions ranging from daily leisure activities to seasonal crop planting to long-term infrastructure investments. During the past 75 years, we have brought billions of dollars in added value to the global economy. We have saved billions more in averted economic losses from weather, climate, and water-related hazards. And we have saved hundreds of thousands of lives. Extreme weather and climate impacts are becoming more intense. We are seeing more frequent and intense heat waves, more devastating storms and floods, more rapidly intensifying tropical cyclones. Between 1970 and 2021, global reported economic losses from weather, climate, and water hazards were a staggering $4.3 trillion. More than 2 million people died. Economic costs continue to soar, but the death toll is falling. Quite simply, we are better at saving lives than ever before. Our top overriding priority is to ensure that early warning systems protect everyone, everywhere. The theme of this year's World Meteorological Day is therefore closing the early warnings gap together. At the halfway point of early warnings for all, we are proud to report progress. As of 2024, 108 countries report having some capacity for multi-hazard early warning systems. This is more than double the 52 countries in 2015. But we need to go farther and we need to go faster. We must innovate together to scale up technologies, stand together to foster collaboration in countries, invest together to create, mobilize, and share resources. Early Warnings for All is now more than an initiative. It is a brand. It is an ambitious target, but we are determined to succeed. We are now expanding support to additional countries beyond the initial 30 focus countries. We are strengthening partnerships with bilateral and multilateral donors, development banks, and climate funds to boost resources and collaboration. We are enhancing regional capacity to ensure lasting impact. We are promoting ownership by placing countries in the driving seat. We are committed to boosting the power of prediction. Technological advances and artificial intelligence promise to revolutionize weather forecasting. But we must level the playing field and ensure that nobody is left behind. We must close the gaps in data and observations. The time is now. By acting now, investing and innovating together, we can fulfill the promise of early warnings for all. It is a human and moral imperative, and it makes economic sense. On a global scale, every dollar invested in early warnings is estimated to result in $9 in net economic benefits. In some regions, it's even higher. I therefore call upon governments worldwide to strengthen investments in national meteorological and hydrological services. This is key to national and international socio-economic development. To conclude, for the past 75 years, WMO has turned science into action for the global good. On this World Meteorological Day, let us reaffirm our commitment to a safer, more sustainable world. We owe it to our children. I thank you.
Thank you, Professor Celeste, for that insightful message. Our next speaker is a strategic leader in climate, weather, and environmental policy with extensive experience in developing integrated programs that enhance early warning systems and disaster preparedness. He has led impactful initiatives that drive sustainable and measurable outcomes in communities at risk. Let us now hear from the Director of the WMO Regional Office for Asia and the Southwest Pacific, Mr. Ben Churchill.
Well, thank you very much, and good morning to you all. Dr. Renato U. Solidum, Junior Secretary of the Department of Science and Technology, Dr. Nathaniel T. Savando, Administrator of the Philippine Atmospheric, Geophysical and Astronomical Services Administration, PAGASA, and Permanent Representative of the Philippines with WMO. Ladies and gentlemen, distinguished guests, further to the inspiring video message from the Secretary General of the World Meteorological Organization, Professor Celeste Saulo, I wish to convey my warmest greetings and congratulations to PAGASA in celebrating the 160th, let me repeat, 160th Philippine National Meteorological Day in conjunction with the 75th World Meteorological Day. Today's commemoration is particularly significant in light of the WMO's State of the Global Climate 2024 report, which confirmed the trend of rising global temperatures and 2024 as the hottest year on record, having crossed the critical 1.5 degrees Celsius threshold temporarily. These rising temperatures are a stark reminder of the increasing frequency and intensity of hazardous weather and climate-related events. Rapidly intensifying tropical cyclones, devastating rainfall, storm surges, flood, deadly droughts, and wildfires are on the rise. And as sea levels are also rising, more and more densely populated coastal areas are exposed to coastal inundation and ocean wave impacts. The societal effects of these events are profound and long-lasting, persisting well after the headlines fade and potentially for many generations to come. Sustainable Development Goal 13 on climate action commits us to take urgent action to combat climate change and its impacts. Progress in this goal underpins progress in all other SDGs. The WMO community is water, energy, and resilient communities. WMO, its members and its partners drive the full value cycle from science all the way through to services to action for the good of society. It advances knowledge of our Earth system, monitors the state of the climate and water resources, provides scientific information to inform greenhouse gas emissions reductions, and delivers climate services and early warnings to support climate adaptation. It is against this backdrop that WMO's celebration of World Meteorological Day gains even greater significance. Every 23rd of March, WMO commemorates the coming into force of the convention establishing WMO in 1950. It showcases the essential contribution of the national meteorological and hydrological services to the safety and well-being of society and is celebrated with activities around the world, including the one we are joining today. The theme for World Meteorological Day 2025, as we've heard, is closing the early warning gap together. At the halfway mark of the Early Warnings for All initiative, which, as you know, aims to ensure that everyone, everywhere, is protected by life-saving early warning systems by 2027, significant progress has been made in saving lives, protecting livelihoods, and strengthening community resilience. However, as climate risks continue to escalate, the urgency to act continues to grow. Entering the next phase of the initiative, partnerships are expanding to accelerate progress. As we deepen our collaboration with bilateral and multilateral donors, climate funds and development banks, support for early warnings efforts is increasing. Regional partners and specialised centres are being leveraged to enhance impact and build lasting capacity. But national ownership remains at the heart of the initiative, with governments leading efforts to strengthen resilience and establish sustainable early warning systems, and Philippines is an excellent example in this case. The Philippines, given its geographic location, plays a crucial role, as I've said. The country faces considerable challenges from various natural hazards, notably tropical cyclones or typhoons, flooding, and landslides. The severity of these challenges was starkly illustrated by the unprecedented typhoon season of 2024, which saw 6 consecutive typhoons batter the archipelago between late October and mid-November. If I recall correctly, 4 typhoons were active at the same time, which caught the attention of the world. Philippines' experience in early warning systems, coordination between PAGASA and national disaster management agencies and civil society, community preparedness, and resilience ensured, however, that loss of life and property damage was kept to a bare minimum. The contributions of PAGASA experts to various WMO initiatives are also invaluable, especially at the regional level. Notably, PAGASA experts have contributed to the annual State of the Climate in the Southwest Pacific reports since 2021, with Mr. Joseph Vasconcillo serving as one of the lead authors for the 2024 edition, which will be released this year. This leadership and active involvement, coupled with the strong national ownership demonstrated by the Philippines and the crucial work of PAGASA, set the stage for impactful progress. In October last year, PAGASA contributed to a successful Asia-Pacific Ministerial Conference on Disaster Risk Reduction and the Regional Early Warnings for All Multi-Stakeholder Forum, which I would like to note included a record number of WMO representatives. More recently, in February this year, PAGASA successfully hosted the 57th session of the SCAP WMO Typhoon Committee in Manila. In addition, with the support of the Green Climate Fund, experts from PAGASA have been helping develop capacity of small island developing states in the Pacific, most recently with training on multi-hazard impact-based forecasts of early warning services in Vanuatu. This is an excellent example of South-South cooperation and should be scaled up and replicated by other countries with similar experience to the Philippines. This will help ensure that the Early Warnings for All initiative is rolled out to all countries, especially the most vulnerable ones, and is truly an initiative for all. In concluding, it is with great anticipation that I look forward to the fruitful discussions on innovations and community-based approaches to improve localised early warning dissemination and response, which this forum will facilitate. And in doing so, I think we can all collectively together make a positive difference. So I thank you very much for your attention, and I hand back to the organisers, and I wish you a very successful event ahead. Thank you very much.
Thank you, Mr. Churchill, for your valuable insights and for WMO's continued support in advancing meteorological capabilities in our region.
So at this point, we would like to invite our distinguished guests and speakers for a group photo to commemorate this special occasion. So first, we'll take a group photo of our guests and speakers here at the venue. So for our participants, kindly remain in your seats as our photographer will move around to take wider shots. Ms. Gail. And for our participants joining us via Zoom, kindly open your cameras too so we can include you in this moment. All right, so for our Zoom participants, kindly open your cameras. All right, so for now we have 7 panels, so kindly hold your smiles. So for the first panel, 1, 2, 3, smile. Second panel, 1, 2, 3, smile. All right, so we have someone from our documenting team gathering the screenshots.
Thank you to everyone for participating in our group photo. Now, we move forward to the main part of our forum, our technical sessions, where we will explore key developments in early warning system and disaster preparedness. The presentation for today's forum are divided into 2 sessions.
So the first session will delve into understanding weather patterns and coastal hazards for improved early warning systems, while the second session will focus on advancements in multi-hazard early warning systems and risk mapping. So before we proceed, we kindly ask our speakers to limit your presentations to 15 minutes. So we will strictly implement this rule so that we can finish on time, as we also have a press conference after this forum. So a 15-minute question and answer portion will also be provided after each session.
All right, without further ado, let us proceed to the first session. To begin, let us welcome our session chair, Ma'am Maria Elena Bitan, Chief of the Farm Weather Services Section of DOST-PAGASA, who will be leading this session. She will be joined by our rapporteur, Rosemary Ann A. Marasigan Forte, who will assist in documenting key insights from our discussions.
Thank you. Thank you very much, Christian and Joanne. Now for the session 1, with me is my rapporteur, Ms. Rosemary Ann Marasigan Fonte. And for the session 1, we have to participate, we have 2 lectures. And each lecturer will be given 20 minutes to present their subject matter. And after the session of the 2 sessions, we will be giving you 15 minutes for the question and answer. So hold on to your questions, and we will be entertaining them after the 2 sessions. Now for the first subject matter expert, we have Ms. Sheila as a weather forecaster in the Marine Meteorological Services section under the Weather Division of PAGASA. She recently earned her Master of Science in Climate and Energy System Engineering from UWA Women's University. Her research interests are tropical cyclones, monsoon, mesoscale meteorology. Currently, her research focuses on improving heavy rainfall prediction during winter monsoon, involving sensitivity experiments using the WRF model and developing a severe weather alert warning system based on the guidance of a WRF forecast. Her recent publication examines the spatial patterns of heavy rainfall and its associated synoptic conditions during the winter monsoon in the Philippines. Ladies and gentlemen, help me to welcome Ms. Sheila May Reyes, a weather specialist of Weather Division.
So good morning, everyone. The title of my presentation is Shear Lines Trigger Heavy Rainfalls in the Philippines During the Winter Monsoon Season. So actually, this is the main finding of our research. And before that, allow me to acknowledge my collaborators and my mentors here, Dr. Sung-Yun Lee, and my advisor, Professor Sung-Ki Park. So let's start. So, as we all know that heavy rainfall is the most common hazard in the country. So, as seen in this figure, you can see that there are two seasons, southwest monsoon season, northeast. For those who doesn't know what is winter monsoon season, I am referring it to the northeast monsoon. So, as you can see that the bulk of the rainfall during and much higher percentage can be observed during the southwest monsoon season, which is the MJJAS. And while for the winter monsoon season, NDJFM, the rainfall is commonly observed in the eastern section of our country. And we all know that most of our heavy rainfall events in the Philippines are observed during the southwest monsoon season or the rainy season. But there are also significant and impactful heavy rainfall events happening during the winter monsoon season. And the problem is there is relatively lack of research focused on the extreme rainfall events and its associated synoptic features during the northeast monsoon season, especially on shear line. So that is the motivation of this research. So there are two objectives. So first is to classify the spatial patterns of heavy rainfall during the winter monsoon season. So the focus here is not the rainy season, but the amihan season. Then second is to identify the associated synoptic weather features that cause those heavy rainfall events. So this is the overview of the data and the methodology that we employed in this study. So we use two data sets. First is the daily rainfall from 55 rain gauge stations of PAGASA. Then the second data set is a satellite-derived precipitation, which is the GPM iMerge with resolution of 0.1 degrees. So the months that are considered here are only November, December, January, and February from 2003 to 2022. So in order for us to identify a heavy rainfall day, so we set a threshold. So a rainfall intensity with 50 millimeters per day, and that rainfall intensity should cover 10% or more than 10% of the region. So if the threshold is satisfied, we considered it as a heavy rainfall day. Then those data that wasn't able to satisfy this threshold was excluded from the analysis. Then we applied the principal component analysis in order to obtain the essential modes, then the K-means clustering. And we arrived to 3 clusters, and each cluster has its own heavy rainfall days. So what we did is we averaged the days here for the composites of rainfall, and then the atmospheric variables obtained from Area 5 with resolution of 0.25 degrees. So let's start with the result of our research. So I think this would be beneficial not only for the forecasters but also for our stakeholders. So this is the spatial heavy rainfall patterns. So this is the result from applying K-means clustering and also averaging the heavy rainfall days in each cluster. So as you can see, so the color here represents the rainfall. So the top row shows the data. So the top shows the spatial distribution using the rain gauge from PAGASA, the rainfall data, while the bottom shows the precipitation data from iMerge. At the get-go, we can see that the result using the two data sets are almost the same. But later, I will show the discrepancy in the rainfall intensity as well as the coverage of this rainfall intensity. So, in general, there are 3 clusters of heavy rainfall events. And each clusters, HRE 1, 2, and 3, shows a distinct spatial rainfall distribution. So, if we are going to only consider the rainfall maxima, we can see a distinct spatial distribution of each cluster. So for example, HRE 1, we can see that more than 50 millimeters of rainfall is observed along the easternmost part of central Luzon, central Philippines, while the cluster 2 is more on the southern part of the Philippines, and then cluster 3, or the heavy rainfall event 3, is more on the northern part. Same as using the iMerge data. But the difference is that there are discrepancies in the rainfall intensity and also the extent of this rainfall intensity. So for example, here in cluster 1, if you are going to focus only for rainfall amount of 75 to 100 millimeters, which you can see here, the top row, so you can see that it's observed here in Sorsogon and Northern Samar. But if you are going to see using the iMerge data, this rainfall extent, the extent of this rainfall intensity covers almost the whole eastern Visayas as well as the northern part or southern part of Bicol region. Then another discrepancy is that using the rain gauge data from PAGASA, so the intensity of, or the heavy rainfall observed in the easternmost part of northern Luzon, you can see that the 75 to 100 millimeters is just a small area. But if we are going to use the iMerge data, there's more than that. So we can see that there's 100 to 125 millimeters of rainfall, and the 75 to 100 is more wider compared to the cluster 3 that the rain gauge data from PAGASA is used, or the rainfall data from PAGASA is used. So that's the discrepancies. So there's, in general, the area of those higher rainfall amount is smaller using the rain gauge data, while there's a wider extent of higher rainfall amounts observed using the iMerge data. And lastly, for the cluster 2, we can see that using, though you cannot see it clearly, but if we zoom it, for the cluster 2 using the rainfall data from PAGASA, the northern part of Mindanao or northern part of Caraga, as well as the Dinagat Islands and Siargao Islands, there is a 125 to 150 millimeters of rainfall there. But if using the iMerge data, there's still small areas, but not as wide compared to the rainfall data from PAGASA. So what is the reason from these discrepancies? So first, iMerge data is a gridded data. So it is more sensitive in capturing the rainfall amount, while the rain gauge from PAGASA is a point-based measurements. So it could be that it would not be able to capture those heavy rainfall or higher amount of rainfall, which happens away from that measurement. And the reason that there's an underestimation or a small areas only of 125 to 150 millimeters of rainfall using the iMerge data is because there's still bias, because this is the remote sense data. It's satellite-derived precipitation. So the problem with iMerge is that there's still a difficulty in capturing higher rainfall amounts, especially those extreme amounts of more than 125 millimeters. But the main finding here to show is that the northern part, because we only have few observations here. That's why using the rainfall data from PAGASA, it wasn't able to capture this kind of spatial distribution of heavy rainfall. This is just a temporal distribution of the clusters. So for the HRE1 or the cluster 1, heavy rainfall event 1, so it is most commonly observed throughout November to February, while cluster 2 mainly December and January, and cluster 3 commonly observed around November and December. And HRE2, the temporal distribution of HRE2 makes sense because during winter monsoon season, especially November, December, January, probably the northeast monsoon is full-blown, so most probably the northeasterlies is more on, propagates more equatorward. So I will explain it later. So this is the synoptic part. So in order to classify each clusters, so we computed for the East Asian Winter Monsoon Index. So we used the 1,000 hectopascal meridional winds. So we used two areas here. Two areas. So you can see that area 1 and area 2, we can see some negative values. And negative values indicates a strong winter monsoon season. It only shows that there's anomalous northerly winds. So you can see that all HRE clusters or heavy rainfall events in the Philippines during winter monsoon season, the result is negative index or indices. And take note of this, that area 2, if we only focus on area 2, and then heavy rainfall event 2, it has the highest index. So it means, so I will explain it later, but this is the finding. So heavy rainfall events occur in the Philippines during a strong East Asian winter monsoon season. So this is we tried, this part answers the second objective. In order to identify the synoptic pattern associated with each clusters. So commonly during winter monsoon season or amihan season, we have this Mongolian-Siberian high, Aleutian low around 60 degrees north, and then we have northeasterly winds, meaning the direction of the wind is northeasterly, which you can see here. And then in the tropics, we can see that the subtropical high, which is the source of the easterly to northeasterly winds. And then the cyclonic vortex. We use the term cyclonic vortex because we only consider the 925 hectopascal. And then the blue dashed line is the shear line. So what you can observe here is that there's a confluence of the northeasterly and easterly flow. And that confluence is what we call shear line. So you can see that in every clusters, so by the way, so the first column we use, so that is based on the heavy rainfall days using the rain gauge data, while the second, the column here uses the heavy rainfall days using the iMerge data. So almost the same, the result is almost the same, but we can see that there's a variation of the location of the shear line. So for the first cluster, we can see that the location of the shear line is around or affecting the central part of the Philippines, while HRA2 is more on the southern part, and then HRA3 is more on the northern part. And this is the vertically integrated moisture flux divergence. So meaning if we have a negative value, there's a convergence in that area. So this is indicated by red, darker red areas. And we can see that the area where the location of the shear line, oh no, yeah, so that's the main findings. So I will just explain to you what is shear line. So what happened is that some frontal system, the stationary front, the cold front, sometimes penetrate in the tropics. But what happened is that the thickness gradient is totally vanishes, or it vanishes, and what remains is the convergence area or the confluence. And that's what we call shear line. So it is commonly observed using the 925 hectopascal winds. So it is characterized by wind shifts, identified by an area of directional wind confluence at the equator side of the cold area where the front terminates. So what I mean is that there's a stationary front, and then at the end of the stationary front or cold front, there's a cold area. And the equator side of that equatorward of that cold area is what we call the shear line, if there's a confluence of the northeasterlies and easterlies. So I will not explain this anymore, but I will show you the summary or the synoptic condition leading to heavy rainfall events, like these heavy rainfall events observed during winter monsoon season. So this is a schematic diagram. So during winter monsoon season, there's a strong East Asian westerly jet, evidenced by a strong and large longitudinal extent of the jet streak. So this is the jet streak. So jet streak is usually we have winds more than 60 meters per second. And that jet streak, because there's a relationship between a larger extent of jet streak to the intensity of the alluvial low. So if there's a larger extent, then there's a more intense alluvial low. So intense formation of alluvial low and Siberian Mongolian high due to strong jet stream. Then if we have an intense alluvial low and a Siberian high, there's a strong east-west pressure difference, resulted in a more southward propagation of strong and cold northeasterly winds. And then the easterly winds from the western North Pacific will have a confluence with the northeasterly. That's why we have the shear line. And then the interaction of the shear line and the low-level cyclonic vortex enhance the convergence and provide lifting. So as you can see, I didn't mention, but because of that convergence, there's a high source of moisture content throughout the vertical column. And this gives a good environment for more convective initiation. So I think that's the point here. So this is for the forecasters and also I think for the disaster managers. So what we observe is that in order to have a heavy rainfall event during the winter monsoon season, a cold surge must prevail, or northeasterly winds must prevail at least 11 meters per second, or near gale force winds. And shear line must interact with low-level cyclonic vortex. If there is an interaction of the shear line and cyclonic vortex, most probably there will be a heavy rainfall event. So that's what we see from the findings. And also, the cyclonic vortex hinders further southward propagation of the northeasterly winds. So what do you mean by this? So for example, for the heavy rainfall event 1 and heavy rainfall event 2, you can see that the cyclonic vortex is more on the southern part of the Philippines. So meaning the northeasterly winds is just above the cyclonic vortex. So the cyclonic vortex will hinder the southward propagation of northeasterly winds. So we can say that if this cyclonic vortex is just located southern part of the Philippines, then most probably the heavy rainfall would probably here in the central part or the northern part, a central part of the Philippines or the northeastern part of Mindanao. And also like this one, another example. So here, the cyclonic vortex is more on the western part. So that's why the shear line is more on the northern part. So we can see that the higher rainfall amount is more on the northern part of the Philippines. So I think this is just last one. So I just want to share the conceptual framework of the Precept 2022 campaign. So they said that the heaviest precipitation occurs where the rainfall rate is highest for
of the storm surge forecasting and warning system and producing local level storm surge hazard maps. These efforts play a crucial role in the advancing of the disaster preparedness, evacuation planning, and the design of the resilience infrastructure to safeguard vulnerable communities. Ladies and gentlemen, let us welcome Ms. Maria Cristina Wilson, Assistant Weather Services Chief of the Numerical Modeling Section of Research, Development, and Training Division.
Hi, good morning everyone. So happy 160th National and 75th World Meteorological Day to all of us. And please allow me to thank the organizer of this scientific forum for giving us this opportunity or chance to share to you the results of our project from the Climate Change Commission. Actually, then it was titled as Generation of Storm Surge Hazard Maps for the Typhoon Pablo affected areas, particularly the municipalities of Boston, Katiil, and Baganga. So for today, I'll be presenting to you of how we develop these local hazard maps, and we give it the title, Development of Local Level Storm Surge Hazard Maps for Potential Use in storm surge evacuation and development planning. So my outline of my presentation would be a little background and introduction, and then the data we used, the methodology we found out and also employed, the results and conclusions. So actually the results of this studies already presented. You may always visit or you may download the paper. So at this point also I would like to acknowledge my co-authors, namely engineers Wilfredo Tuazon and Sheila Snyder, and also Ms. Jehan Panti Without their support also, or without their help, it wouldn't be successfully completed. And also other personnel from HT Mears before Nick and Ted Santos. So as we all know, the Western North Pacific is a breeding ground for tropical cyclones. So an estimated of around 26 tropical cyclones originates from this area, from the Western North Pacific, and around 19 to 20 on the average enter the Philippine area of responsibility. And around 6 to 7 of those tropical cyclones makes landfall, and one of the associated hazards of tropical cyclone is storm surge. And may I also mention that for the third year, Philippines has registered highest as the country's most exposed and at least to natural hazards. That is from the World Meteorological Index. So Philippines is not spared to the wrath of the storm surge. Well, actually, for the study area, which is at Davao Oriental, which is at the southern part of Mindanao or of the Philippines. So we all know that this part of the country is not frequently visited by tropical cyclone. Well, in fact, only 9 tropical cyclones from 1948 to 2013 actually passed through this province. So it is also due to Typhoon Pablo that some areas of the Davao Oriental experienced storm surges. So the Climate Change Commission then, in partnership with UNDP and also funded by Australian government, they had this project Climate Twin Phoenix, and PAGASA is tasked to develop the storm surge hazard maps. So these are the data which we usually need when developing storm surge hazard map. We need to have the digital elevation model, the bathymetry and tide data, the storm surge heights, and as modeled or as from the experience of the residents. But back then, I thought this would be enough to develop the storm surge hazard maps. But I was mistaken because along the way, as we do the process, we've discovered that there are much to do. Like, for example, for the DEM or the digital elevation model, this has to be adjusted to the mean sea level. And to do that, we've done, the field operations, including the geodetic leveling and the topographic survey. And also, for the whole process, we did the hydrographic survey as well, and the tidal survey. And then the simulations of the storm surge model, we had the JMA storm surge model and the Delft 3D model suite, and storm surge then followed by storm surge inundation mapping, and also and validation of the storm surge model, storm surge hazard maps. And those include storm surge high water mapping and ground field validation. So as you can see, this is the process. And then, so for the DEM, the need to adjust this to the mean sea level, actually the DEM is the reflection, or it reflects the physical condition of the place. And for this project, we use actually LiDAR and IFSAR. And LiDAR is produced from series of point measurements with associated heights above the ellipsoid or the WGS-84 ellipsoid. So for many coastal applications, including flood risk mapping, the LiDAR elevations are transformed from ellipsoid heights to orthometric heights. Orthometric heights are based on the geoid, an equipotential surface defined by the Earth's gravity field, approximately equal to the mean sea level. And to obtain the orthometric heights, an adjustment must be made for the local vertical separation between the ellipsoid and the geoid. So this shows the picture at the left or the right, at my right, shows the three basic geodetic surfaces. These are the geoid, the earth or the topographic surface, and the ellipsoids. So the ellipsoid defines the mathematical surface approximating the physical reality while simplifying the geometry. So actually, the true shape naman ng Earth, it's not ellipse or hindi siya perfectly na ellipse. Marami siyang mga contours, that's the geoid. And the height referring to the mean sea level is the orthometric height. So in areas around the coasts, the mean sea level is often adopted as the basis for reckoning the heights. So usually, we would hear, in reference to mean sea level, we would consider that. One of the major arguments for the use of the orthometric height is its relationship with ocean or the water body. It's said that direction of flow of fluid is not controlled by height. It is actually the force of gravity that governs fluid flow, not height. Therefore, selection of a height system that neglects gravity or does not use it rigorously allows the possibility of fluids appearing to flow up hills. So, this shows the relationship between the ellipsoidal height, the geoid or the mean sea level, and undulation value or the geoid height. So from this one, we have the ellipsoid, which is the perfect ellipse, which is a mathematical, parang it's just a display. And also, we have the geoid, the red one, and the topography or our topography. So, okay. So, in a while, I'll show you the process which we made to be able to get the orthometric height and also the undulation value, which we use for the adjustment of the DEMs. So, in here, it shows actually, this is one of just part of the area where we conducted the study. So we did a differential leveling activity, and that was conducted to transfer the mean sea level elevation from a known tidal benchmark. And this is a process of vertical surveying which determines height or elevations above mean sea level surface. And the geoid corresponds to the mean sea level of the open ocean. So there is this, okay. Wala na yatang battery to. Okay. I see, sir. Okay. Anyway, this is a location wherein a known benchmark is located. So there is this known benchmark, and we have to. Actually, it was we also collaborated with NAMRIA then in doing this one. NAMRIA is supposed to install a subordinate tide gauge in this area, but since there is no, they need the elevation of the instrument from that area, they need to transfer the benchmark or the mohon, or which to reference that to the mean sea level. So they did the differential leveling activity to be able to transfer the information of the benchmark to that area. And this is how they did it. So that is shown there, that there is the location of the known benchmark, and they transferred that until they reach the coastal area. So this is the one which I am mentioning, the tidal or the benchmark or reliable benchmark, also from NAMRIA. It gives information of the location as well as the elevation with reference to the mean sea level. Then, alongside, we also conducted the topographic survey. And we used the Real-Time Kinematic Global Navigation Satellite System, or the RTK-GNSS, which belongs to a group of satellite referencing survey instruments known as differential global positioning systems. So this consists of a base receiver and a rover receiver, which both communicates with GPS satellites and each other. It is also equipped with real-time kinematic functionality, which increases more accuracy of the surveyed positions. So, and the RTK receivers make use of the much higher frequency satellite carrier signal to reduce error of measurements to the nearest millimeters. That one is the base receiver, and this one is the rover. So this one, okay. So initial stage of the topographic survey includes identification and establishment of benchmarks. For this one, before we left for Davao Oriental, we need to have requested already or already have the idea where the benchmark is. Otherwise, we'll have to spend a lot of time looking for the mohons or the benchmarks. So kailangan namin magpatabas ng mga dahon, ng mga we need to clean the place to find the benchmarks. And then this is an essential part in any terrain survey, which involves referencing of field measurements to a standard datum to allow compatibility between the observations and existing data sets. And this is achieved by measuring the position of known coordinates relative to the chosen datum during the field survey. And the base is usually set up and on a known benchmark, while the rover is carried in areas where there are risks for storm surges to capture relevant natural and anthropogenic features such as beach face, dunes, and seawalls. And sometimes the rover receiver is mounted on tricycles or habal-habal to capture more features or in areas where larger vehicles can't enter. And this is the hydrographic survey, which is also one of the important data to accurately model storm surge. Then I have to go faster because, okay, then this is the installation of the tidal station or the subordinate tide station, wherein we have to do also tide survey. So the tide survey was conducted in parallel with bathymetric data acquisition. And every hour, data were logged in the portable tide gauge data logger and then downloaded at the end of the agreed observation period. And this is also used to correct the raw sounding or bathymetry data. And then for the model of the storm surge heights, we use the JMA storm surge model and the Delft 3D. And, okay. That's already the mapping. Okay. So for the storm surge inundation mapping, and these are presented in the form of maps or in the form of like magazine maps. So it shows here the inundation maps, inundation depths and extents above ground as a result of the storm surge and wave models used and as mapped using the bathtub method. And okay, the map part shows the inundation depth and extents of storm surge flood of the barangay that it represents. And the index map is the map of the municipality to which the barangay belongs, with the red box indicating the location of the barangay with reference to the municipality. And it also has the legend that shows yellow for less than 1,
amber for more than 1 to 2, and red for more than 2 to 3, and violet for more than 3 meters. This is just an example. And this is some of the results of the topographic survey. The color-shaded relief image of the DEM and the red triangles represent the locations of carrier phase DGPS points used to confirm the DEM. And the blue line represents the shoreline. And this is for the Kabasagan DEM and Katiil DEM. So those were the areas where we conducted the topographic survey. And then for Creek Katiil DEM. And then for the hydrographic survey, this was conducted near shore areas of the municipalities of Boston, Katiil, and Baganga, Davao Oriental, and resulted to about 620 kilometers of main sounding lines and 62 kilometers of cross-line surveys. And the spacing between sounding lines for the single beam was 100 meters throughout the survey. And the northern southern limits are 7 degrees 26 minutes 53.98 seconds north to 7 degrees 53 minutes 13.20 north latitude. And then these are some of the results which we eventually was able to create out of the topographic and bathymetric survey. We were able to develop a seamless digital terrain model in the vicinity. The black line represents the cross-section in the area. Those line represents the cross-section, and these are the bathymetric profile. Actually, the bathymetric profile gives you an idea of the shape of the topography as well as the bathymetry of the data. Okay, 1 minute left. So I have to go faster. So actually, one of the takeaways also, or the advantage of having conducted the survey is be able to have a visualization or an idea of the type of beach which these areas have. Okay. So here we have the coastal profile in Barangay Kabasagan, which can be classified as exposed littoral cliff coast, and predominantly rocky coastlines are adjacent to littoral coast. Coastal bathymetry in this area is slightly deeper as compared to the Kawayanan and Boston area. And also here, coastal profile, and then the bathymetry profile, and the highest observed storm surge height in this area with reference to the relative mean sea level was 3.0 to 3.3 meters in Purok, Daisy, and Rosal. So this is a barangay with fringing reefs in the area. So, okay. Anyway, just want to show you also the reefs. The example of this is the validation. These are the magazine type hazard guide developed. This is the storm surge hazard guide for Katiil, Davao. So it shows a brief introduction of the place as well as it's information for storm surges and also the tropical cyclone warning system, the storm surge hazard maps, and how to use the storm surge hazard maps. And this is the history of the Typhoon Pablo. And here we were able to do or develop that for Typhoon Pablo, for Barangay Mainit, for the barangay of Katiil. Here, there. And then, konti na lang po. And this is also, we also made hazard map for worst case scenarios such as Yolanda. Okay. Okay. And also. So I think that's it. Thank you. And for the
Thank you very much, Ms. Christy Uson, for that very informative presentation regarding the storm surge mapping in Davao, particularly due to the occurrence of Tropical Cyclone Pablo. Now we go on to the question and answer. For the question and answer, may we request those who interested to put in their questions, please state your name and affiliation in order for you to, for the documentation purpose. Can we see hands for the questions? Miss Hazel?
So, magandang umaga, si Hazel Tanchuling po sa Rice Watch Action Network. So, I appreciate the presentations, no? It's more of in the early warning chain or elements, parang it strengthens further yung first part and maybe the second part, the first part of early warning, which is the detection and analysis and observations, no? And even siguro yung dun sa second presentation, yung disaster risk knowledge. Pero po yung, meron po bang, is there, I would like to hear kung ano yung naging, dun sa closing the early warning gap, dun po sa side ng disaster risk communication and improving the preparedness actions of the community. Yung dun sa storm surge, may specific na area kasi siya. So halimbawa yung Katiilan ba yun? Yung sa Surigao po yata. So paano po siya na-improve yung preparedness actions ng mga community sa baba? So magandang marinig po yun. Dito sa shear line, hindi ko alam kung meron na kasi bago siya sa pandinig ng mga tao. Pero how was it, ano ang plan to improve yung use of it down to the community level or yung mga specific sectors so that we will improve preparedness actions para consistent with yung ating anong tawag mo dyan? Consistent with the theme na closing early warning gap. So, kasi yun yung gap. Yung malakas kayo sa part ng detection, syempre you are the agency. But what we need is yung doon sa part ng the community and then mobilizing, maybe improving communications and improving preparedness actions. Maraming salamat po.
Thank you very much, Ms. Hazel. For the storm surge, maybe request Ms. Christie for the comments, reaction.
Good morning. Thank you, Ms. Hazel. So, clarify ko lang what has improved the community. Yeah. So, actually, the one which I presented a while ago is a result of the project from the Project Climate Twin Phoenix, and these were distributed to the community. Actually, one of the role of the project is actually to disseminate this to the community for them to use. And also, siguro in continuation, we also hope to do this with the other parts of the country. So right now we have also the project from the multi-hazards impact-based forecasting and early warning system. So hopefully we could do more. Actually for Palo, we have a project there, and we hope to also come up with storm surge hazard maps on a local level.
Thank you very much, Ms. Christine. Now for the shear line, may we ask Ms. Sheila, please?
Yeah, so actually, the audience that we want to target on this research is actually included the disaster managers. But the action might be, or the information that we can obtain from this study for the disaster managers is the information. Like we already show the spatial distribution. So once PAGASA will say that the shear line is affecting the central part of the Philippines, then the disaster managers or the LGUs will have the idea of the areas that might have higher rainfall amounts. I think that's the immediate application from this study. So it's like a more knowledge to the LGUs that once we have this kind of shear line or weather system affecting on a certain part, then these areas might likely receive a higher rainfall amounts.
Okay. Thank you very much, Ms. Sheila. Any questions? Yes, sir. Sir, you can use this mic. You can use that mic, please.
Hello. Hello po, good morning. Janjan Abel po from Makati DRMO. For my question is for Ms. Sheila. Thank you so much. Actually, yung research is namangha ko kasi ang galing ng research yung in terms of shear line. So my question is awa ko kung tama yung or pasok siya dun sa research, but my question is there something ba na pagka nagkakaroon ng climate variations, pagka lumalakas ba ang El Nino, La Nina, and neutral, nagkakaroon ba ng variations din ang shear lines? Kung meron bang epekto, kagaya po ng nangyari kanina na winter monsoon na malakas yung epekto dito sa Mindanao, may kinalaman din ba yung climate variation in terms of pag El Nino, weak El Nino or strong El Nino, weak La Nina or strong La Nina, and then neutral? Thank you po.
Actually, hindi namin yon kinonsider. So, out of the objective na yon, kaya hindi namin kinonsider yon. So, hindi ko po masasagot directly. Pero, ang masasabi ko lang, kasi yung shear line kasi is synoptic driven. So, once na mas intense yung Siberian high mo, tsaka yung alluvial load, kahit yung jet stream. So, possible din po na mas more southward and mas intense po yung cold surge. But in terms of climate variation, hindi pa po namin yon na re-research or na-explore. So, siguro, for further study or research opportunities po yun.
Thank you very much, Ms. Sheila. Any additional comments, sir? Do you have some additional response? Okay. Yes, sir. Ariel, please.
The question is for Ms. Sheila. Did you try to check some incidents, shear line heavy rainfall events like that one in Katarman, same incidents, just to check whether what your results match the actual incidents?
So actually we do that because after this study we do some sensitivity studies in WRF. So we choose certain events that closely match the spatial distribution. So if you look at the cluster 2, if you can go back to my presentation. So the cluster 2 or the heavy rainfall event 2 is closer to the Katarman, just recent, 2023? November 19 to 2023. So you can see that the maximum rainfall is almost the same when we again, go back to the spatial or the isohyoidal rainfall produced by PAGASA. So, kung titingnan niyo po yun, almost the same po yung result. Kung titingnan niyo po actually po yung paper is published na po. So, there's a detailed information there, especially for the weather forecasters, kung paano po i-assess. So, pwede niyo pong tingnan doon at basahin po. So, yun. So, meron. Each clusters, meron po siyang representation na almost the same po sa na-observe natin.
Okay, thank you very much, Ms. Sheila. One last question from Engineer Alfredo Kiblat, sir, and also from Dr. Servando. Okay.
Question, suggestion for Ms. Sheila. The recent incident, flash floods in Palawan, you might consider also in your study breaking the record of the highest daily rainfall of 300 plus from the old 295 I think in 1975. So there was due to shear line, and I think there was a low pressure area, a western portion of Palawan, that one of the factors to be considered for the heavy rainfall of the effect of the shear line.
Actually,
Thank you very much for the... yes, Miss Sheila.
Actually, sir, I think you should do some specific case study for that. Kasi yung akin kasi general po kasi siya, sir. So yung buong winter monsoon season po yung focus ng study. So kailangan mo ng specific event at tingnan natin, sir, kung tumagos ba talaga yung shear line or yung effect po is more on the low pressure area. So I think there should be a case study for that.
Thank you very much, Ms. Sheila. Engineer Kiblat. Yes, Dr. Sarbando, please.
My question kay Sheila also. Thank you, Sheila, for a very nice presentation. By the way, congratulations because Ms. Sheila Reyes just came back from his master's degree, I think, in Korea. Yeah, your presentation actually is very relevant to the theme, given the limited publications or articles when it comes to rainfall, heavy rainfall events associated with northeast monsoon compared to the southwest monsoon na widely publicized or there are available literature. And of course, the lack or the absence of forecasting tool in monitoring this event. Kasi during the Habagat or southwest monsoon, the western part of Luzon, including Metro Manila, are flooded. During the northeast monsoon, is the eastern side, like eastern Mindanao, may mga landslides, including northeastern Luzon. Now, given the number of factors that may cause this northeast monsoon surge, like wind anomaly, mentioned the northeasterly wind should be higher than 11 MPS, probably temperature anomaly or gradient kasi kapag malamig in the north, di ba, associated na rin ng strong northeasterly. And maybe pressure gradient, you mentioned the Siberian high and the cyclonic vortex, which is low pressure system in the southern part of the Philippines. And probably climate variability, and I mentioned yung El Nino, La Nina, but on a short-term variability like in GO could have influence also on the rainfall events. Can we put this into one like index just for the sake of the predictability of this event so that we just look at just one value rather than analyzing the whole synoptic situation?
I think from being a forecaster or the perspective from a forecaster, I think there's no one way lang, sir. So kailangan mo talagang i-assess yung other parameters. But given if we have time to research for that, then why not? Possible, no? I will not say it's not possible, but kung itatry po natin, baka merong magandang result.
Some other countries are using this monsoon index, and we can adapt or formulate a localized. We have already, we're actually, currently we're working on the localized southwest monsoon index, but for the northeast monsoon, sometimes there's a challenge because yung relatively less rainfall, but when there's a surge of rainfall, matindi yung impacts. So we really need to come up with this kind of prediction system.
Now, thank you very much. If you have further questions, can you just, because of the limited time, sinasenyasan ako, dala-dala you can approach our lecturers as subject matter experts later on. Please, sorry for that. We need to control the time now because we still have 3 presentations coming. And I will now turn over the microphone to our host, Peace Sir Vic.
So thank you, everyone. So in the interest of time, we will be having a working break and to proceed to the next session. So to our guests, Our colleagues will be distributing the snacks during the second session. And as for our fellow PAGASA employees, our snacks will be provided by our respective divisions later.
Up next, we have our second session chaired by Dr. Joseph Q. Basconcillo with Ms. Crystal Ann Valerie M. Villasica as the rapporteur.
Okay, maraming salamat Christian and then Joanne for the introduction. So this is the second session of our scientific forum. So we prepared 3 presentations for you, particularly in bridging the early warning gap from this scientific presentation. So papunta na po tayo dun sa exciting part. So this is now, this set of presentations are catered specifically for our disaster managers who are with us right now. Palakpakan po natin yung ating mga disaster managers who are with right now. So again, in the interest of time check, it's already 10:51. So we have here our rapporteur, Ms. Crystal Ann Valerie Villasica. And reminder for our 3 presenters, you have 20 minutes. You are given 20 minutes for your presentation. So to start with, let me begin by introducing our first speaker. He is the Philippine Field Manager for the PRISM project. The title of her presentation is COP, so that would be Community of Practice, Practitioner Inundation Scenarios Mapping Project. So she has provided us a recording. Dr. Lau, please. Round of applause for Dr. Loris Hamero. Okay. Thank you. Again, in the interest of time, would it be possible, we can skip for now Dr. Loris Hamero, and then we can proceed with the second presentation first. So may we call on the second presenter, that would be Mr. Edward P. Kahukom, the project manager of the Multi-Hazard Impact-Based Forecasting and Early Warning System. For his presentation, also Multi-Hazard Impact-Based Forecasting and Early Warning System for the Philippine project. Mr. Edward Kahukom, please. Round of applause for Mr. Edward Kahukom.
Hello, good morning, everyone. And again, I'm Edward Kahukom, and allow me to present the Multi-Hazard Impact-Based Forecasting and Early Warning Systems project for the Philippines and how it addresses the current gaps in early warning system. So as a briefer, we all know that the Philippines is very rich in vibrant culture and natural beauty. But as you know, the Philippines face a stark reality, disasters. So each year, we face numerous and destructive natural hazards, and one of which are severe winds, storm surges, floodings, and landslides. So during the onset of the 21st century, so we have experienced numerous destructive hydrometeorological events. Particularly in 2009, we experienced tropical storm Ondoy that caused severe flooding. In 2012, we experienced Super Typhoon Pablo, as mentioned by our previous speakers, and it caused strong winds in the area. In 2013, we also experienced Super Typhoon Yolanda that caused massive storm surges in Leyte. And in 27, in Mindanao, we also experienced tropical cyclone or duha or landslides. And to date, Super Typhoon Haiyan remains one of the deadliest and most destructive natural disasters in Philippine history. So this Super Typhoon Haiyan caused billions and millions of damages and casualties. And it considers, as I've mentioned, one of the most destructive typhoons in the Philippines. So at that time, Philippine Atmospheric or PAGASA was very confident that they had provided accurate and timely forecast. But this triggers the question, what went wrong? So for the purposes of this presentation, allow me to share with you some of the key identified gaps in IBF EWS. First, there was a disconnect between forecast and actions. So warnings were issued, but they did not translate into timely and actionable early actions at the community level. Second, there was a limited resources, the local level. So many LGUs lacked the necessary resources to implement proactive DRR measures. Then lastly, there was weak links between the preparedness and response because current policies prioritizes response and recovery rather than preparedness and response. So that key gaps served as our inspiration to develop the multi-hazard impact-based forecasting and early warning systems project for the Philippines, or we call it the MIFUSE. So back in 2019, we developed the MIFUSE project concept note, and the same year we have, or the GCF board approved the first ever Green Climate Fund project in the country. So while it was approved November 14, 2019, operationally, we just implemented the first GCR project last February 14, 2023. So as I've mentioned, the MIFUSE project is funded by the Green Climate Fund. So GCF is a multilateral financing entity of the UNFCCC. And as a key component of the Paris Agreement, it helps the developing country realize and achieve their nationally determined contributions, or the NDCs. So annually, they provide funding support under the adaptation and mitigation projects. So the MIFUSE project aims to strengthen the Philippines' ability to adjust to climate impacts and implement long-term climate risk reduction and adaptation measures. And it will build on best practices in multi-hazard early warning system and link with forecast-based action to minimize the impacts on the ground. So this includes climate resilient development planning and investment. So as I've mentioned, we started in 2019 and we're expected to be completed on April 5, 2027. So this is the overall goal of the MIFUSE project, to translate the current threshold-based forecasting to impact-based forecasting. Or as you know, we want to translate or transpose what the weather will be to what the weather will do. Why? Because in impact-based forecasting, ayaw yata next. Ayan. So in impact-based forecasting, we would like to emphasize more on the potential impacts of the weather events on the people, property, and infrastructure, unlike the traditional weather forecasting that only or primarily focuses on the meteorological data. And in impact-based forecasting, we also want to utilize graphics, color-coded maps, and icons to convey risk levels and potential impacts. And in terms of communication, in IBF, we want to clearly communicate the risks rather than the hazards and exposure associated with weather events and expected impacts. And in IBF, we would also like to provide more actionable information, helping individuals and communities make informed decisions. So in IBF EWS project, we'll be using these three key information: the risk matrix, the risk map, and then the impact and response tables. So in the next slides, I'll explain how these key elements work together to close the gaps in traditional early warning system, ensuring that forecasts are not just about predicting the weather, but also triggering timely and effective responses. So currently, the MIFUSE project operates in the 4 project sites, most vulnerable project sites in the Philippines: Tuguegarao City, Legazpi City, Palo Leyte, New Bataan, and Davao de Oro. And we focus on the 5 major hazards: severe wind, flood, landslides, and storm surges, plus the debris flow. So we have 9 executing entity, PAGASA being the lead executing entity. We have also partners from MGB, OCD, DILG, and WFP. And the direct access entity of our projects, Land Bank of the Philippines. So we have 4 outputs. The output 1 focuses on the delivery of all technical outputs of the project. For the output 2, here we will develop the national and localized impact and response tables, supported by a knowledge decision support system. So under the output 3, here we will develop the national and local capacities in implementing IBF and EWS. And also would like to highlight here that in output 3, we'll develop early action protocols and anticipatory action measures. And all of the technical outputs to the early action protocols will be mainstreamed and institutionalized in the output 4 of the project, which is being headed by the DILG, or Department of Interior and Local Government, with its co-lead, the Office of Civil Defense. So as I've mentioned, GCF, the MIFUS is the first GCF project in the Philippines, but it's not the first IBF project in the country. I'm glad that Makati City is here because way back 2019, PAGASA has also implemented WCSSP project. So it's an impact-based forecasting project na nagpo-focus to 2 project sites, initial project sites. That's Metro Cebu and Metro Manila. So going back to the key identified gaps, and given the project background, the following slides outline the specific project interventions conducted and being conducted to bridge the gap in IBF AWS. So for the purposes of this presentation, allow me to present to you how we bridge the gap first in the disconnect between forecasts and actions. So, okay, developing impact-based forecast is not a simple task, as you know. So transforming the threshold-based forecast into impact-based forecast requires a lot of technical backgrounds and a lot of technical actions to trigger not only response, but also anticipatory action at the community level. So weather forecasts are only truly effective if it translates into early actions. And in IBF EWS project, we don't want to just capacitate the weather forecasters as the provider of the weather information, but we also want to capacitate the last mile end users of the project to have the ability to interpret the data being issued by the forecasters for their use for early response and early actions. That's how we want to bridge the gap, in IBF EWS. We want to connect the provider of the weather information to the user of the weather information from the weather translation or from the weather information hazard translation to response actions. Okay, so how do we do that? First, in the MIFUS project, we developed the national impact tables and response tables. So here's the national impact tables developed for flood, storm surge, landslide and debris flow, and also for severe wind. So as you noticed, and as you observe, we have already developed and identified specific impact statements for each impact level. And moving forward, these statements will be incorporated into PAGASA's warning forecast to trigger specific early actions before the onset of the event. So, but how did we develop these impact tables, and how did we ensure that the impact and response tables are first people-centered and second sector-specific? So, okay, here's the brief timeline of how we developed the national impact tables. First, from 2023 to 2024, we engaged with the LGU stakeholders across the 4 project sites that I've mentioned earlier to understand their perspectives on various impacts. So through this discussion, we gathered insights into their recommended responses based on their experiences and lessons learned from past disasters happened in their area. So from 2024, since meron pa tayong kinonduct ng mga operational activities, this was followed by a series of introductory meetings on the MIFUS project, specifically with the members of the NDRIMC. So this meeting aimed to align expectations, present key accomplishments, and outline of the necessary actions, not only at the national level, but of course, for the local government units. And then right after that, in the last week of January 2025, we took steps to ensure that the relevant and accountable sectors were informed and actively involved. So to finalize the impact tables, we conducted sectoral focus group discussion aimed at developing specific impact indicators and impact statements. So we conducted FGDs with transportation sectors, health and safety sector, lifeline and utilities, agriculture and aquaculture, and of course, society and economy. So just last January 27 to 30, we have already finalized the national impact tables to be disseminated and to be rolled out to the 4 project sites of the project. So this is the sample of the national response tables developed by the project. So this was based from the national impact tables developed by the MIFUS project. So as you can observe, here in the national response tables developed by our colleagues from the Office of the Civil Defense, they have already developed the national and regional actions up to the proposed local minimum actions before the onset of the event or 3 days before the landfall of the, say for example, typhoon, to the onset and to the post-disaster response. So the agency concerned per impact statement and response statement were also identified. And currently, this version is being localized at the 4 project site of the MIFUS project. So overall, next slide, please. Ayan. So overall, this is the main goal po no, ng MIFUS project. And this is the future directions and plans of the MIFUS project. So the MIFUS project is designed to provide impact-based forecasts at least 3 days before the onset of an event or before the impacts will be felt. So this ensures no, that the communities and decision makers have sufficient lead time to take necessary anticipatory actions. So moving forward, PAGASA forecast will gradually shift from traditional weather bulletins to a more actionable impact-based forecast using color-coded maps and risk matrices similar to what you see on the screen. So for example, if PAGASA detects a severe weather event expected to impact Santa Ana, Cagayan on November 7, as early as November 4, you will already have the information on what impacts you will be experiencing on the next 3 days and what actions to take. Anong actions yung kailangan yung i-undertake to minimize the risk and potential damages and losses. So these are the key activities that the MIFUS project is implementing to bridge the gap between forecast and action. And this particular intervention ensures that early warning will lead to timely and effective interventions on the ground, which will then enable a more proactive and coordinated disaster response efforts. So going back to the key identified gaps identified earlier, the second gap in the IBF EWS relates to the limited local resources for early action. So currently, the Local Disaster Risk Management Fund or the LDRMF remain underutilized. So due to various constraints, no? So one of the major challenges is the lack of institutional mechanisms to effectively mobilize these resources for proactive response. So currently, there are approved and signed JMCs or the Joint Memorandum Circulars to ensure local resources are available before and during the onset of the event. However, these available JMCs are currently limiting. So LGUs cannot implement policies, programs, and projects because of the fear of COA disallowances. So to address this gap and to empower our LGUs with local resources for anticipatory action, we assisted the Office of Civil Defense in revising this present JMC 2013 and 2014-1. So what are the initiatives of the project to address the gaps in this JMC 2013-1? So in the JMC 2013-1 is the guide to the LGUs on the allocation and use of local DRMF. And under the Section 21 of RA 10121, LDRMF should not be less than 5% no, of the estimated revenue from the regular sources of the LGU, and it shall be set aside to support disaster risk management activities. So of the 5%, 70% should be allocated to the disaster prevention, mitigation, preparedness, response, and rehabilitation and recovery, and 30% should be allocated for quick response fund for relief and recovery programs. And currently, while very facilitating yung aim nung JMC 2013-1, may mga na-identify pa rin na gaps dito sa JMC 2013-1. Some of the gaps ay majority of the LGUs were assessed to have LDRMF utilization rate. Unimplemented programs, project and activities as identified in the LDRIMP. And etong mga nakita nating gaps na na-identify during sectoral consultation. So to address that, we assisted OCD in revising the current JMC. And here are the revisions for the allocations for the LDRMF. We've included the allocations for the procurement of equipment, devices, and tools for risk assessment, early warning systems and anticipatory action, and also for the conduct of the DRRCCA capacity building, research and development, and science-based technology activities for rapid onset and slow onset hazards. And also, since the JMC 2013-1 focused on the 4 pillars of DRRM, particularly the disaster prevention, mitigation, preparedness, response, and recovery, we've also included set of sample projects, programs, and activities under each pillar. So say, for example, for the disaster prevention and mitigation, we've included increased structural integrity, housing, building, and critical infrastructure, and also the institutionalized, timely, responsive, context, and culture-specific early warning system. And in the disaster preparedness, we've included also enhanced risk awareness and risk-informed decision and actions of the government. So we also recognize that report writing and submission of reports are time-consuming and labor-intensive for LGUs. Hence, we also introduced some templates and reporting formats to our LGUs to assist them for seamless submission of the reports, particularly post-disaster. So, yung mga roles and responsibilities that I've mentioned earlier seems to be overwhelming. So, the JMC 2014-1 is here to establish and operationalize LDRMOs, including the BDRMCs. However, this JMC 2014-1 has also its gap, particularly the limited budget, the majority of the DRMO staff are contract-based, designated positions are multitasking, and also the generalized function and responsibilities of the LDRMOs. So to address this, we also introduced revisions in the JMC 2014-1, particularly under the policy guidelines, the organization and composition, the position titles, qualifications, standards, and salary grades, and for the technical staff of the LDRMO, particularly in their function and responsibilities in research and planning, administration and training, operations and warning, and even at the responsibilities of each agency, we've refined each roles and responsibilities na identify doon sa nag-i-implement ng JMC 2014-1. So going back to the key identified gaps, at the national level, we've identified that the current systems and policies in place are reactive. So currently, we don't have the proactive approach to implement DRR measures. So next slide, please. So to address the gaps in the limited proactive approaches, here's the Memorandum 60 or the MC60 of the NDRIMC or the Revised Declaration of the State of Imminent Disaster. So for the MC60, as you can notice, we have the criteria for the declaration of state of calamity. But as you can observe, the approaches and the criteria are reactive DRRM. So what we want here is to transform the reactive DRRM into proactive DRRM. And here's the proposed interventions of the project to address the gap in the EWS. So thanks to our NGO partners, particularly the START Network and the FAO, for providing or for facilitating the declaration of the State of Imminent Disaster Act, now formally known as the House Bill 9935. So the House Bill 9935 seeks to institutionalize anticipatory action to mitigate the impacts of hazard before they strike, or particularly in the context of growing climate crisis. So this bill allows the national government agencies and the LGUs to declare state of imminent disaster for areas such as the following: when any or one of the following criteria are met, a significant population is projected to need emergency assistance, critical infrastructure or facilities expected to be damaged, lifeline systems are anticipated to be disrupted. So once an imminent disaster is declared, national and local responses can be mobilized preemptively, and this enable actions like prepositioning relief goods, reinforcing infrastructure, and evacuating vulnerable population before disaster hits, rather than waiting for the aftermath. So who shall declare the national state of imminent disaster? For national, it would be, of course, the President of the Philippines. For the local, it would be the mayors or the local chief executives. What's the basis of the declaration? Of course, it will be the PIDRA. Then the recommending body, it would be the NDRIMC or the RDRIMC. And then, of course, the criteria for the declaration will be the forecasts and projections issued by PAGASA. So the sources of the funding are the following, but let's all be informed that this House Bill 9935 implements no regret approach. So if a hazard forecast change, the bill adopts no regrets policy, meaning that any anticipatory action taken are designed to still benefit the communities even if disaster does not occur as predicted. So as of March 15, the House Bill 9935 remains a proposed bill, and it's still under the House of Representatives and Congress review. But we're still hoping to have this approved by this year. So before I end my presentation, I would also like to highlight key challenges in implementing the IBF EWS. Of course, we depend on the forecast uncertainties. So forecasts are not always 100% accurate. So the anticipatory action approaches must also involve probabilistic responses. Second, institutional readiness, because as I've mentioned, we need barangay level data. So the institutions or the LGUs to be partnered with the MEVIUS project should be institutionally ready. And of course, the approval and acceptance of the key decision makers. And in order to address that, we must ensure, as mentioned by our secretary, multi-sectoral collaboration. We must also advocate for improved policies and multi-sectoral collaborations. So, yun po. Thank you so much. And if you have questions, please let us know.
Thank you very much, Mr. Edward Cajucom. Round of applause again for Mr. Edward P. Cajucom. So before we head on to the next presenter, let me acknowledge first our friends via online. So we have about 122 participants via Facebook Live, and we have about 878 via YouTube. So round of applause for them. Thank you. Round of applause. And then we have for the Zoom participants, we have 194 participants. So napakarami po natin kasama ngayong araw na to for the scientific forum. So for our next presenter, kanina po nagkaroon tayo ng problema, but again, for our next presenter, that would be, if we are ready. Dr. Lau, are you here?
Yes, I'm here.
Hi, Dr. Lau. Good morning. All right. We are now preparing your presentation. So we're going to share it now. Okay, so for our next presentation, that would be Dr. Loris Hamero, the Philippine Field Manager for PRISM PH, for her presentation, Community of Practice, Practitioner Inundation Scenarios Mapping, or PRISM PH project. A round of applause for Dr. Loris Hamero, please.
Hi everyone, I'm back. Hopefully you can hear me clearly. Yes, apologies for the technical glitch earlier. And this time, I'll be sharing with you all about the PRISM project, or the Practitioner Inundation Scenarios Mapping project. So just to introduce myself a little bit, so I'm Loris Hamero, and my home organization is the Manila Observatory. But I'm also part of PEERS, which is a community of practitioners. It's actually the first global community of practitioners pulling in together all of the local planners that are involved in building coastal resilience. Next slide, please. So the PRISM is actually an international project led by PEERS, and it started off in Latin America and Caribbean, and their second study scientists here in the Philippines. So internationally, the project partners involve peers. Our technical support is coming from NASA Sea Level Change Team, as well as the Aspen Global Change Institute. And here in the Philippines, the project is funded by World Bank through their Pro Blue initiative. Next slide. Right, so Prism PH is actually a short-term project. We just started in August last year and ended this month. So given the short timeline, we identified 2 specific objectives that we want to be able to achieve through the project. So the first objective is to co-produce inundation maps with our pilot LGUs. So emphasis on the term co-produce. And these maps should be based on the best available science from the IPCC, sea level rise projections. So to help us do that, we are receiving technical support from the NASA Sea Level Change Team. So they are offering help in terms of doing the sea level rise modeling, but working with NASA, we are also able to access the wealth of Earth observation data that they have. So that's a crucial partnership that we have in the project. And the second objective, we don't want to be only providing the maps and leaving our pilot LGUs to figure it out for themselves. As a community of practitioner peers would want to also offer continuous support for practitioners so that we are able to translate scientific information and really help when it comes to local planning and implementation. Next, please. Right, so this is like the co-production process in a gist. So the first phase, we started with an outreach. Basically, what we did here in the Philippines, I reached out to the different national government agencies, our own technical experts when it comes to coastal hazards and sea level rise, and of course, our local government partners. And just getting the insights of everyone regarding what they need specifically in terms of localized sea level rise information. So after reaching out to everyone, we proceeded with the co-production phase, which is where we selected emission scenarios together, as well as inundation scenarios together. So I'll be talking more about that later. So after selecting all of the scenarios, we did the mapping, of course. And then earlier this month for the co-production phase 2, we met right outside PAGASA in Quezon City. We got together, looked at all of the draft maps, saw if there's anything that we would like to improve on the maps for them to be not only useful, but most importantly, usable for our practitioners. And in the implementation phase, as I said, we're really interested in following up on how the maps are being used, and if possible, offering customized advice on the implementation of the different adaptation strategies that our local government partners are considering. So next slide, please. Right, so here in the Philippines, we are super duper happy to be able to partner with many national government agencies, and foremost, of course, is PAGASA. So thank you so much to the PAGASA team for being one of the biggest partners that we have in the Philippines. Aside from PAGASA, we are also collaborating with NAMRIA, MGB, PhilSA, and DSUD. And on the policy making side, we have DNR and CCC, and of course, my home organization, Manila Observatory. Next slide. Then at the local level, we actually ended up selecting 4 pilot study sites. So even the selection process of the pilot study site in a collaborative manner. So in the end, we selected Manila Bay, and our partner there specifically is Navotas City, Mactan Island, Lapu-Lapu City, Danahon Bank. So if you're not familiar, Danahon Bank is actually a double barrier reef that is in the waters of Bohol, Cebu, and Southern Leyte. So for this project, we mainly worked with the Bohol side of the Danahon Bank. So recently, 10 municipalities got together and created a management council. So we are working with them. And then last but not the least, Siargao Island, specifically the municipality of Belconnen. earlier, I talked about the first step in the co-production, being able to select sections together. So this is quite a busy slide, so I will do my best to break it down slowly for everyone. First of all, we looked at scenarios from 2050, 2070, and 2100. So remember, we are trying to produce local sea level rise information. So for just to share, we actually have a sea level rise analysis in the Philippine National Adaptation Plan. But this analysis is at the regional level and also mainly consider 2030 as 2050. So for the project to really add value, we wanted to look beyond 2050, going to the end of the century. And from the scientific perspective, it also makes sense because if we look at the sea level change, they actually diverge depending on the emission pathway beyond after 2050. So we can clearly see the difference in the emissions. For sea level rise, as you know, under CMIP 6, the latest set of climate projections, there are 5 scenarios for the SSPs. So out of the 5, we selected 2, together with PAGASA and our local government partner. The first scenario we chose is SSP 2-4.5, which is usually what we refer to as the middle of the road or moderate emission scenario. And under this scenario, we are looking at a future world that is around 2.7 degrees Celsius warmer. So that's the global warming level by 2100. Now, the IPCC, considering all of the current global policies and actions and ambitions, this figure, 2.7 degrees, is the most likely scenario that we are looking at in the future. So under FSP 2-4.5, we looked at 2 values. So remember, we live in a future world and we don't know exactly what will happen. So it is important to consider a range of values so that we can prepare accordingly. In this instance, us and our partners selected the median value, which is the 50th percentile, and also the upper end of the likely range, which is the 83rd percentile. So this middle of the road scenario is very useful for us, especially when we are planning for development and hopefully low carbon development. For disaster risk management, it's also important for us to see more extreme kind of scenarios, what we refer to as high impact, low likelihood scenario. So in this case, that would be SSP 5-8.5, or what we refer to as the very high emission scenario, where by 2100 we are looking at more than 4 degrees Celsius global warming level. As I said, this is extreme, this is unlikely, but still, in our disaster risk management efforts, there is a need for us to also consider what the high impact, low likelihood scenario. Also here we looked at the median value and the high end value, which is the 90. When we were talking with all of our partners, we understood that our local government units are interested as well in storm surge risks and how sea level rise can potentially aggravate inundation caused by storm surge. So for this, we did a still water elevation map. It's just basically a snapshot of what the extent of inundation might look like given a certain level. Then we work together with the team in determining the scenario for storm surge. So for Navota City, that's 2 meters. Lapan City in the Nahon Bank, that's 4.5 meters. And for the municipality of Del Carmen, 5 meters. So just to note, these are all based on historical values, but again, it's just one number per area, right? Just one scenario out of the range of values that I get. So just a quick note, we are looking at above mean high water, so it means that they are already considering the high tide value, average high tide, and it also reflects DLM for the vertical land. Right, so this is just the example of the maps. So this is Mactan Island, and here you can see 2100 under the high emission scenario. The red areas are the connected inundation, and the yellow areas are the disconnected inundation. So the connected inundation is directly as a pathway to the water line, and we see from the maps that as sea level changes and increases, the disconnected inundation actually slowly becomes connected. Right, so this next slide is showing a steam map, but with 4.5 meters storm surge for Mactan. Okay, 4.5 meter surge for Mactan Island, and you can see here the level of how much more devastating inundation is with storm surge and sea level rise combined. Next slide. All right, so these are just some photos from the workshop that we had earlier this month. As you can see, the local governments were able to really examine the maps, interact with them. Next slide, please. So of course we asked, how we can improve the maps, but more importantly, we were able to create storylines for what would happen in 2050, and then in 2070, and then in 2100 with sea level rise as well as storm surge. And I wanted to note that this is actually a 3-day workshop. And the first day we spent doing a technical workshop where we invited our own technical experts in the Philippines so that our partners from the NASA Sea Level Change team could actually share all of the science behind sea level rise mapping, modeling, and all of those nitty-gritty so we could build our own local capacity to do this type of work. So next slide, please. Okay, next slide. All right, perfect. Next slide. All right. So just a quick note. So during the workshop, we actually talked about sea level rise, of course, but also recognizing that there are many other coastal hazards that could potentially have a compounding effect with sea level rise. So this picture shows here the vote that our participants casted when it comes to what their risk priorities are, and I thought it was very interesting to share that with you today. So the top risk priorities are sea level rise and subsidence, sea level rise and flooding, and sea level rise and storm surge. And quickly following those three are tidal flooding and sea level rise as a slow onset event. Okay, next slide, please. So just a little bit of note on tidal flooding, since especially we are interested in early warning systems. So I just wanted to share this particular example from Navotas City. So out of the 4 pilot study sites, 3 right now are already experiencing tidal flooding. So in Navotas City, they already have an early warning system, local system in place. So this really caught my attention. This is their high tide alert maps. So every month they distribute these maps and post them in all of the barangay halls in Navotas City. And what this says is that whenever the high tides hit 1.5 meters and above, then they are on high alert. But our colleagues from Navotas specifically told us that flooding becomes a big issue for them whenever high tides reach 1.8 meters, plus there is intense rainfall event as well. So this just shows that there really is a need for early warning, even in the case of sea level rise, especially now that we are already starting to experience tidal flooding. For the Nahon Bank, for example, they are one of the most extreme cases of tidal flooding in the world today. They experience tidal flooding about half of the year. And when they were hit by Typhoon Odette in December 2021, it happened around peak tide, so that the storm surge were much more devastating in the experience of the Nahon Bank. So next slide, please. Okay, so I think this is my last slide. So again, I just wanted to emphasize the need for continuous partnerships. It's a short-term project, but is basically just a proof of concept of how this can be done in a co-production process working with our local practitioners. This is a huge milestone for us here in the Philippines. It's one of our earliest efforts to produce localized sea level rise information, and we have much more to do. The Philippines has a very long coastline, and we want to be able to expand this to all of the local governments that need this information. So again, just emphasis on partnership as a very important part of the co-production process, and super grateful to PAGASA, especially for, again, being a valuable partner in this project. So with that, thank you so much, and back to our moderator, Dr. Joseph. Thank you.
All right. Thank you very much, Dr. Loris Hamero. Palakpakan po natin. Round of applause for Dr. Loris Hamero. That was a very interesting Doc Lau, as regard to the sea level rise. And we have been talking about this since last week, during the workshop that we conducted for the PRISM. This is Joseph, by the way, if you cannot see me. So we are live via Facebook, via YouTube, and of course, via Zoom. And as we speak, we already have, again, 188 participants via Zoom. And then via Facebook, we have about, let me check, about 89 participants via Facebook and about 800 plus via YouTube. And there are some questions made before the chat box in our Zoom. And some are asking about the presentation. So we're going to ask for the access for those presentations, and we're going to send them to you, those presentations, as soon as we get access and permission from the presenters themselves. So without further ado, let us proceed with the next presentation. Our next presentation is going to be provided by Mr. Chencho Dorji, the FAO International CIS Specialist. His presentation is on experiences and challenges in the establishment of early warning systems. Round of applause for Mr. Dorji.
Thank you. Maganda umaga. Good morning, ladies and gentlemen. It's a pleasure for me to be here and sharing experiences. And first, at the outset, congratulations to PAGASA for the 160 days celebration. It's a remarkable journey, securing society, making safe and resilient society. And also, congratulations to everyone for the 175th WMO Day. So I'll be very brief, and since this is the last presentation, I'll try to wrap up, what earlier presenters have spoken, because they are in a way all related. So I'll try to wrap up and try to tweak my presentation now. So I'll be talking in 3 sections. The first one, maybe going back and then reflect on what is early warning system, because we have been talking a lot since morning on early warning system. And then I'll share 2 specific case studies or examples that I have been involved, especially in terms of early warning system. And then finally, I'll wrap up with some of the key takeaways that you can reflect on while you work for the early warning system or while you implement the early warning system. Next, please. So, what is early warning system? So, the WMO and the UNDR defines early warning system, as an integrated system that detects, forecasts, assess risk, communicates and prepares the community or people to take timely action and then reduce disaster risk before the hazard occurs. So that's the early warning. So early warning should be, not just information, but an actionable information. So these are the 4 pillars of early warning for all. You can actually browsed this or have accessed this on WMO's website, as well as the partners of WMO on the early warning for all. So there are 4 key pillars. So developing disaster risk knowledge, then you have observation, monitoring, analysis, and forecasting, where PAGASA plays a key role here in the second component. Then you have warning, dissemination, and communication. Then you have preparedness and response capabilities. So these are the 4 main pillars. And as you know, in the early speakers have showcased how they have worked, in terms of building resilience in the community. So in a way, all these 4 pillars have somehow addressed in their works, but that may not be fully covered. But in a way, each of these pillars will have to be addressed, and as you have seen, it has been addressed. So in a nutshell, the early warning system should be multi-hazard. So meaning it should cover a multi-hazard. So say, for example, if you want to have early warning for typhoon, so you cannot only focus on wind, because typhoon is a multi-hazard. So wind, high heavy rainfall, then other associated hazards like floods, landslide, and so on. So it has to be multi-hazard and end-to-end. So meaning, it should start from, like, for example, observation, detection, and so on and so forth until response, and preparedness, response to the until the last mile users. So it should not end abruptly, and then it should be people-centric. Again, meaning, so when you design or implement early warning system, the need of the people should be first, not what, if you are a provider of early warning, you should not be influenced by what you want to do. Rather, it should be influenced by what those users want. So now getting into the specifics, as I said, I'll focus on 2 case studies. So maybe from the oceans, I'll take you to the mountains for a while. So implementing GLOF EWS in Bhutan. So GLOF is Glacier Lake Outburst Flood in Bhutan. So as you have seen in the picture, Bhutan is a mountainous country, and it has a lot of glaciers and glacier lakes. Next, please. So why, GLOF or Glacier Lake Outburst Flood early warning systems? Bhutan's geography is so precarious, so that it makes it vulnerable to the Glacier Lake Outburst Flood. As you have seen in this picture, the picture above, these are the glaciers and glacier lakes in the upstream or the source of the major rivers of Bhutan. And then the map you see and the red dotted are the location of the settlements along the river valleys. So 70% of Bhutan's settlements are along the river basin. So early warning system is very crucial, especially for GLOF for Bhutan. And we have had a lot of histories, but among which a massive GLOF occurred in 1994, and it has caused especially damages in the infrastructures, and also around 20 deaths. At present, based on the recent studies, there are more than 500 glacier lakes in the Bhutan, and of which 17 are classified as potentially dangerous. So meaning at any time it can burst. So this is the scenario. Next, please. So how did this early warning on GLOF has been implemented? So it was a multi-stakeholder approach. So meaning a lot of agencies were involved, among which the key agencies are the NCHM, that is something like PAGASA, then disaster management, the local government, and the local communities. The key part of the stakeholder is the local communities, because they are the ones who are vulnerable, and they are the ones whose needs has to be addressed. And the establishment of national and subnational committees for early warning. So these committees would support the planning, support the implementation, and also, in the long run, in terms of ownership of the early warning system. Then to monitor and detect these, the glacier events, then automatic weather stations, automatic water level stations were installed, and then the control room, monitoring rooms were established where people are monitoring 24/7. As you know, communication is a challenge, especially in the mountainous terrain. So, backups communications like satellites were installed so that even in the events of hazard, you can still have uninterrupted communication. And then the key part for consistency, and also for the continuous building of knowledge so that the communities are always on their toes and they can respond anytime. So there's a periodic awareness and also mob drills to ensure they're always prepared. So next, please. So the current status, so I was able to get this from my former colleagues at the Hydromet Agency in Bhutan. So they were saying that the early warning system now has been almost more than 20 years plus. So through their experience, improvement in technology, so what they're saying is now there's an enhanced detection accuracy, especially even the glacier rock slidings into the glacier lakes, and it's become reliable. Then there's a strong preparedness. Communities are more aware of these threats of the glacier, and lives and assets were protected. So that's what they're saying is they're still having recurring glacier lake outburst floods, although they are not massive. But then because of this EWS, they were able to warn people before the glacier water reaches the community. So that's the impact. So they were able to protect lives especially, and then that's it because of the faster response, and then also with the knowledge people has developed greater resilience. And then what they're going on is, as you have seen in the earlier map, a lot of rivers and glaciers, so they are scaling up and replicating this in other river basins. And the future improvements, we could take advantage of the advancing technologies like AI and other technologies that may evolve in future. So next, please. So there are challenges. So while you implement this kind of early warning system, especially in the mountains, and I see similar scenarios when I visit across Philippines, especially in the mountainous provinces, and also you have big dams. You could have similar experiences because although the natural cost will be different, but the initial flow of the flood water, especially the Glove and dam, are almost similar. So inaccessible glaciers. So this is still a big challenge. High cost and logistical challenges. So one key aspect is communication issues. So the option are have a satellite communication, or maybe in future there could be other options to overcome these communication challenges. And then once you have this early warning system with sirens and other warning systems, false alarm is something that you cannot avoid. But then how you can do is you can always improve with better technology, and also analyzing the false data, and also based on your experience, what is not going well and how you can actually improve based on your experiences. And community reluctance is always there, so that's why it's always critical to involve the participants, the communities from the beginning. So this has to be addressed through continuous education. So continuous education should be there if your early warning or any of your early warning system has to be sustained. And then resource constraints, I think this is something that will go on, financial and as well as human resource gaps. So the strong institutional commitment is required, from the political aspects, as well as even the individual agencies, if the early warning systems or the tools that you are developing has to be sustained. Next, please. So then I'll briefly talk on the decision support system for early warning and early action for agriculture. So for your information, for some who haven't heard of adapting Philippine agriculture to climate change, which is being jointly implemented by Department of Agriculture, PAGASA, and Food and Agriculture Organization. So we'll be developing a similar kind of system for our farmers so that they get, forewarning and they can take proactive actions before disaster strikes them, or, in a way we could minimize the, impacts of the disasters. Next, please. So why these decision support systems? Or in other words, people call it as a platform, they call it a website. The name doesn't matter, but as long as it serves its purpose. So how does these kind of decision support systems help the stakeholders or the users? Is it enhances and expands the uptake, use of weather and climate services. And then the key part is it actually empowers and also enables, it gives you additional intelligence to the users to make actionable decisions based on the weather, climate, or other information, so that you can take actionable information and also overcome the challenges of climate variability and change. So this is so how this system works is it will take in weather, climate, or water, or the data you have, and then sector data, and also in terms of hazard data, and all these will be integrated, and then it will help you provide advisories. Then through this you can provide alerts to the users, and also it enhances how you communicate these warnings and other information to the users. Next, please. So the key partners, especially in terms of developing early warning, early warnings for agriculture. So the main player would be the agriculture sector. Then NHMS is National Meteorological and Hydrological Services, that is PAGASA here in Philippines. And then you'll have the ICT agencies, the local government units, research, extensions, farmers group, academia, and NGOs and private sectors. Of course, these are the key players, but in some instances, this may not be limited to this list of agencies. Next, please. So an example of the decision support system, I got it from my friend in Bhutan just yesterday. So this is the, the front page of the decision support system. So, it should provide early warning information. So, one aspect, early warning aspects, as you have seen in the pillar, the risk knowledge. So if you look at other, other modules there, it will provide you, the information about hazard. So, you have alerts like heavy rainfall alert, heat alert, and frost. So in a way and then you also provides access to range of data and forecast. So in Philippine context, it can be from PAGASA. And then for disease, for pests. So this is a kind of a one-stop shop, for the weather information, for sector information. It integrates everything on one platform and enhances, the dissemination. In a way, it actually builds an intelligent system where it actually empowers the users, both the sector experts and the users, to take proactive action. Next, please. So, it will allow a lot of, it will give you a lot of tools and, systems to view and, see the warnings or communicate those warnings and information. Next, please. I'll just run it through. And you can have localized, here in the context of Philippines, you can have provincial, kind of advisories, even the municipal. So then you can have past weather, what has happened in the past week, and what is going to happen. So all these warnings and information can be, disseminated through this kind of system. Next, please. And then this system, as I said in the beginning, it will enhance the communication, It actually addresses the gaps in the traditional mode of communication. So the system can send group emails automatically to all the, the stakeholders who are responsible for taking actions. And then you'll have, it is also linked to, the mobile applications. And these mobile applications are supported even by AI chatbots, which will respond to some of the queries of the users. So next, please. So challenges and lessons learned from this designing of this decision support system for agriculture. So institutional coordination is a key thing here. So, a lot of, especially in terms of sector to sector, there's a limited coordination between agencies like PAGASA and other sectors. So there should be, kind of a regular engagement, and also it's recommended that you have a kind of a, expert group or technical working group, so that there's an ownership and then you get to know people much better. And then obviously when it comes to these kind of systems, especially whether in climate or disaster, gaps in skills, and then agrometeorology or even IT is limited. So there should be continuous capacity building, training, and awareness. And then also limited access to weather and climate. So climate data and forecast. So for the record, all what is being provided from PAGASA may not be adequate for you. So that's what I'm trying to tell. But through consultative methods, engaging with each other, PAGASA understanding your need, you understanding PAGASA's capacities and capability, you can always come up with a way out to fill those gaps and limitations. And then also, similarly, the data gap in other sector would be, same in terms of, the strategies that you apply. And then, of course, the capacity building is key thing, so continuous learning should be there. So finally, next please, this is my last slide. So finally, this is the main takeaway, but this is not limited to the 2 case studies that I presented, but based on my experience over South Asia, Bhutan, and then now in Philippines. So in terms of establishing early warning system, or rather with the WMO's DO theme, like filling the gap, closing the gap of early warning. So in order to do that, the first critical thing is involve sector agencies early in the design and implementation, so that it becomes people-centric or user-centric. It's not like the provider's target, but you can actually achieve what people want or what users want if you can involve them in the beginning. And then contextualize, so which means what you are providing should be location specific, or it should be localized. And then, of course, awareness and capacity building, as I mentioned earlier. And then your early warning should address multi-hazard, to have a comprehensive coverage. But the key recommendation would be here, although you'll be addressing multi-hazard, but take stepwise, in a phase-wise. So for example, in typhoon, the first phase you could focus on wind, and then heavy rainfall and landslide and so on and so forth. Why? Because it reduces complexity. You can, also it enhances the proper allocation of resources, because then if you try to do everything together, it increases, the complexities, and then confusions and challenges are more. So it's always recommended to take phase-wise, then ensure consistency, and it should be culturally acceptable, especially here in the context of Philippines, where you have, indigenous communities, where you have different communities, different culture aspects. So while developing and implementing early warning, so you should always keep in mind and design, based on their cultural acceptance. So in other way, you could also integrate local knowledge. And just one I want to, focus on, that is importance of coordinating with neighboring countries for regional hazards. So like in the beginning, we are talking about, the northeast monsoons and even El Nino, ENSOs, and all those things. So it's not just a Philippine focus event. So it's a global phenomena. So in order to understand and also respond more collectively, so you need to coordinate with the regional partners, so that you can have a knowledge transfer, exchange of knowledge, technological transfer to provide better early warning system. So finally, again, coming back to the sustainability, because most of the early warning systems are project-based. And then what happens is, once the project closes, the early warning systems also phases out, and they are no more functional or, although they are functional, but there's nobody to take care. So it's very critical that, or crucial, that you have to institutionalize early warning system in the national framework so that it ensures sustainability. Yeah, thank you.
Thank you very much, Mr. Chenjo Dory. So that wraps up our session 2 for our scientific forum. So in the interest of time, we can no longer entertain questions or comments or manifestation from our participants. However, there are contact details provided in the presentations, and if you want to clarify some things as regards to their presentations, please feel free to contact our 3 presenters. So round of applause for Dr. Loris Hamero, please. Mr. Edward P. Kahukom. Thank you, sir. And then Mr. Chenjo Dorji. Thank you, sir. Maraming salamat po. And I'll now turn it over to our host this morning. Thank you.
All right, so thank you everyone for your participation in our discussions. So at this point, we would like to recognize our esteemed speakers for their invaluable contributions. Let us now proceed with the awarding of certificates. May we call on Ma'am Thelma A. Cinco, the Chief of the Climatology and Agri-Meteorology Division of DOST-PAGASA, to lead the presentation of certificates.
Good noon. So, umabot na ng 12. So, ano na lang natin. Maraming salamat sa ating lahat and also from the viewers. Thank you very much. And to award, and thank you to our resource persons. I will read the citation. Certificate of Appreciation is presented to our Ms. Sila May R. Reyes for sharing her expertise as a resource speaker during the Scientific Forum in celebration of the 160th National and 75th World Meteorological Day, with the theme, Closing the Early Warning Gap Together. Given this 21st day of March 2025 at PAGASA Central Office, Quezon City, Philippines. Signed, Dr. Nathaniel T. Servando. And also, in the interest of time, can we also call the other resource persons to come? Ay, Doc Mar, sana. And the same certificate goes to Miss Christina Uson. Ay, say. Kayo na mag-abot. This goes to Mr. Edward P. Kahukom. And to Mr. Senchu Dorji. Thank you. Thank you. And online, we also have a certificate to Ms. Dr. Loris D. Jamero. Picture. We also want to give a certificate of appreciation to our speaker earlier, Mr. Ben Churchill. Thank you.
Thank you, Ma'am Thelma, and thank you once again to our speakers for sharing your expertise. Today's forum has emphasized the significance of collaborative efforts in addressing the gaps in early warning systems, ensuring that no community is left behind.
As we conclude our discussions, we are now invite the Deputy Administrator for Research and Development of DOST-PAGASA, Dr. Marcelino Q. Villafuerte, to deliver the closing remarks.
Hi, thank you very much. Magandang tanghali po sa ating lahat. Of course, to those our speakers, no, 5 speakers, and to those who are present here in Amihan Conference Room, who made your time to attend our scientific forum, and also to those joining us online. I think more than 1,000 already, ano. So thank you very much for your time. They say that good things also come to an end, and we have unfortunately came to the conclusion of our event this morning, our scientific forum. So in celebration of, this is of course in part of our celebration of the 160th National and 75th World Meteorological Day. In the past several years, actually this forum has become a regular activity for the Met Day celebration. And also for this year, this once again is held among the lined-up activities. So we continue to invite everyone to stay with us for the rest of the day. Actually, we are also holding a press conference on the opposite side of this floor as part of our celebration of the National and World Meteorological Day. And then we also have some exhibit booths downstairs, no, on the ground. So please feel free to attend also and visit some of our partners. And as we conclude this event, let me express our heartfelt appreciation and gratitude to all who took part in this special gathering. Of course, to all our 5 speakers who unselfishly shared their expertise with us. So to all our colleagues in the DOST-PAGASA, particularly our colleagues from the field stations, no, from different PRSDs, thank you very much for finding your time, no, to attend to our scientific forum. And to all our participants who joined us this morning in this scientific forum and staying with us for the whole duration of the forum, maraming salamat po sa inyong lahat. In spite of the very limited time, which is only about 3 hours, I'm confident that everyone learned a lot and gained valuable information, no? Actually, including myself, I learned a lot from our speakers. So congratulations for the success of this event. And then I hope to, and I look forward to seeing you again next year. Again, my heartfelt thanks to everyone. Keep safe and stay informed. Magandang hapon po.
Thank you, Doc Mar, for your thoughtful words and for reinforcing the key takeaways from today's forum. Your message serves as a strong reminder of your shared responsibility in bringing the early warning gap. With that, we officially close today's forum. We extend our deepest gratitude to our speakers and all the participants for making this event a success.
Let's continue working together towards a more resilient and weather-prepared nation. Once again, I am Joanne Mayadelino.
And I am Christian Villalon, wishing you a
happy 160th and 75th
World Meteorological Day.
All right, thank you and happy lunch, everyone.
Sorry.